So recently we've just been looking at the classes of alcohol and how we can use chemical reactions to differentiate them. So what were the two main reactions we can use to differentiate primaries, secondaries, tertiaries? What can we use? Oxidation, which is what we're going to look at today, and what else? Lucas reagent, which is a type of substitution reaction. Okay, the substitution one's quite easy because it gives you one possible product, but actually the oxidation, depending on the strength of your oxidizing agent, has got a couple of possibilities if it's a primary alcohol. Also, you probably found that in the reactions that you did yesterday, you had to heat a few of them or be very patient with them. Okay, so if you'd heated them, they would happen a lot faster. There's a small problem with heating organic compounds, and they're what we call volatile. Volatile means that they can become a gas very easily, which is really convenient when we want to use them as fuels because gases burn really well if they've got carbon in them. So that's what makes them really good fuels. They can be gasified or evaporated very easily, and then the gas will burn. So that's convenient if we want to burn them. It's not so convenient if we just want to react them and get a product that we can use. Because when we heat them, we lose our reagents and often some of our products into the air. So we have to have a way to capture the stuff even though we're heating it. You could put a lid on it. That's a bit of a problem too, because gases take up a lot more space than liquids or solids. So if you put a lid on it, you're going to increase pressure, and eventually the lid's going to pop or the vessel's going to explode. So not a good thing to do. So it needs to be what we call an open system where nothing can escape, which seems completely impossible, but it's not. The process that we use is called reflux. And what we do is we heat a flask. It's either going to be round bottomed or pear-shaped. Pear-shaped is like that, but like a love heart. Like a real heart. I'm going to go with round bottomed. And then our heat source is going to go underneath it. Inside it, we're going to put something to spread the heat out. Usually it's just little bits of ceramic, because ceramic will heat up faster than the liquid, and then they bounce around in the liquid, and of course give their heat to the liquid, the particles that they touch. Then we've got our thing here. Now you can see it's still an open system. There's no lid on it. Which means as I heat this, things are going to escape out into the air, and if they're in the air, they can't react. So I haven't achieved anything good yet. Until I put a thing on it called a condenser, which, as the name suggests, turns the vapour back into a liquid. And the way that it works is you've got an inner tube, which is connected to this, and an outer tube that is not. And the outer tube has got a hose coming in and a hose coming out. Sorry, I think I've done that the wrong way. A hose coming in, a hose coming out. So what we've got is we've got water being able to go into the outer tube, while the inner tube is where the vapour will be. Okay? And if I put cold water in here at the bottom, what's going to happen to the temperature of that water when it hit, what's going to happen to the temperature of the water though? It'll cool down or heat up, because the gas in here is hot, so will the inner tube glass. They'll both be hot. The cold water touches them, and the heat gets transferred from the glass and the gas inside it into the water, heating the water up. And if that energy is being lost by the stuff in here, what's going to happen to the speed of the particles in the inner tube? So we've got the organic compounds in here that we want are losing heat energy. What will happen to their speed? Slow down, and what will happen to them then? Condense. Okay? So they'll turn back into a liquid, and they'll drip back down here. What can happen down here? Reactions. So what happens is it vaporizes, and then it condenses back down. It vaporizes, it condenses back down. But every now and then, it vaporizes, condenses, and reacts. And the hotter this gets, the more likely it is that when it falls back down, it will react. This process is called reflux. And in theory, the only thing that should escape out of here is water vapour. Because eventually the water vapour will be so hot that it can't recondense in time in there. But everything with a boiling point lower than 100 should, in theory, come back down here. We find in practice that's not what happens. You end up getting yields of 70, 80%, which means some of the organics do still escape. It's not perfect. But it's a lot better than if I got you to do it without the condenser, you'd end up getting yields of about 10%, 15%. So it's a lot better. All right? So this is a really good process to get a chemical reaction to be completed, which is really good if you've got something like a secondary alcohol being oxidized, because what's that going to turn into? Ketone, well done. And that's the end of the line. Ketones can't be oxidized, so that's it, end of the road. If it was a primary alcohol, they oxidize first of all into a thing called an aldehyde, and then this oxidizes through to be a carboxylic acid. So there's two possible products. If I do it by reflux, I end up with only this, because as the aldehyde evaporates and drops back down, then it can continue to react. Okay? Once all the alcohol and all the aldehyde has been oxidized to this, no further reaction can occur. And then I just have to be able to separate the carboxylic acid out of my mixture in here, so it can be used as a starting product for something else, or used to show the properties of carboxylic acids. So reflux will help me get to the final thing, but it won't help me get the aldehyde. So what I've got to look at are the properties of what I've got here to work out how to get that. Now my challenge that I'm going to give you today is I'm going to give you propan-1-ol, or 1-propanol, and I'm going to give you the equipment required to make this and this using the same chemical reaction. We're using a weak oxidizer, or it's not weak, but it's not as strong as permanganate. We're not using permanganate for a reason. Permanganate is such a strong oxidizing agent, you're unlikely to get the aldehyde. It'll be very hard to get. So we're going to use a slightly weaker one, dichromate, which should allow you, it's also got a really easy to see colour change, which will allow you to see the colour change easily from orange to bluey green. And it should allow you to collect some aldehyde if you do one method, and it should allow you to collect the carboxylic acid with another. Now, for that we need some properties, so I'm going to give you some hints on how to do this. This reaction here is the final product. Okay? This is what both of them will turn into. So I can use reflux for that. That's easy. The tricky one is this one. Now, what I want you to look at is a particular part of each of these chemicals, the OH. Now, when an oxygen and a hydrogen are bound together, there is the potential for a thing called a hydrogen bond. Hydrogen bonding is even stronger than when things are polar. Okay, you know how polar molecules have quite strong, for intermolecular forces, or van der Waals, they're pretty strong, have quite strong forces between them. These are way stronger, the hydrogen bonds. So what they're caused by is the lone pair of electrons on the oxygen and its high electronegativity so there's the rest of the compound, there's the rest of the compound. What happens is that lone pair and that hydrogen form quite a strong bond that we show with lines like that, called a hydrogen bond. And this is the strongest form of, as it were, polar intermolecular bond. Alright, so it's that force between two polar molecules. It's the strongest of those types of things. If you go any much stronger, it becomes an ionic bond or a covalent bond or something like that, which is intramolecular or intraparticle. So it's quite strong, and you'll notice that both of these have this OH, which will allow them to have this very strong bond between particles. What would that do to their boiling points and melting points? They're about the same size. They're all about the same size molecules. They've got 3 carbons in their chain. They've got oxygens, they've got hydrogens. So what we call dispersion forces, so just the fact that they will be attracted to each other by random chance, what will this do to the boiling points of these two relative to this one? Higher. Good, because the bonding between the particles is stronger. This is your big hint. These two have got higher boiling points than this one. So reflux isn't going to work, but you could use the same equipment in a different way to collect this. There's another piece of equipment you'll need, but I'll let you look into that. Okay. There are hints on your OneNote, if you want to have a look in there. Okay. I haven't put those hints on your blog yet. That'll go with this video once we've worked it out. So your challenge today is, I'm going to give you some propane 1-ol. You're going to use sulfuric acid from down the back to acidify your potassium dichromate. You'll need some little bits of broken ceramic bowls, basically, to spread the heat out evenly. And then, let's hope I can hold this up without making a complete mess. And you've got a thing called quick fit apparatus. So what you've got is, rather than a round bottom, I'm going to give you a pear-shaped flask. There's your condenser with the hoses on it. And just a hint for you, you might need that thing there. Okay, just a wee hint for you that you might need that piece there. Okay, so my challenge to you is to try to devise two methods to use the same reagents and pretty much the same apparatus to get two different products. The test, by the way, for this one, if you're successful, is you'll then do the Benedict's test to see if you were successful. If this turns Benedict's from blue to brick red, you've got it right. If it doesn't, you need to try again. Yeah.